very excited to present on this topic today. It's I think probably it's probably the most important kind of subfield of machine learning for the sciences. And I'll just say I'm very sorry I couldn't be there. Basically what happened is I was an idiot and I didn't know that passports have like this 90-day rule before they expire. You can't like travel with it. So I like found that out at the airport on Saturday night. But yeah, so hopefully I can still teach you some things even though it's over Zoom. And I'm happy to have like follow-up discussions over email because I can't be there in person. So my name is Miles Cranmer. I'm assistant professor at the University of Cambridge in Dampton, Iowa, as part of this new data-intensive science master's program. I'm also at the Flatiron Institute in New York. So I'll just give a quick kind of advertisement because I have to for my research group. So I work on, I guess, kind of broadly interpretable techniques for doing machine learning in the sciences. So we have different papers on kind of going from planetary dynamics to galaxy evolution to fluid turbulence. The one theme is that we kind of try to build new methods that are fundamentally interpretable. Yeah, I'll just quickly mention, so we have this new initiative called, we don't really have a name for it yet. It's called Foundation Models for Science. The idea is that we want to build like the GPT of science. So we're building this at Flatiron Institute, Cambridge, and we want to train this massive model on like 500 GPUs. There's future PhD postdoc opportunities if you're interested. Happy to chat more about that. Okay, so that's the advertisement part. So now let's get into the lecture. What is interpretable? Like what makes a machine learning model interpretable? So at the end of the day, I think I want machine learning to give me models in a language I can understand. So, you know, I want insights into existing models like scientific discovery. I want to understand new things that I'm missing in my physics. I want to understand biases and maybe learn shortcuts of my models that I need to deal with. And I also want to place stronger physics motivated priors on the space of potential machine learning models. So this is my lecture outline. So basically I'm going to review the basic concepts. We're going to split interpretable machine learning into two areas. The first is inherently interpretable models. So that's models that they're designed from the ground up to be interpretable, and then post hoc methods. So these are like, you have this nasty black box model and you want to understand what it's doing. At the end, we'll look through some examples and then we'll have a Q&A. And then tomorrow we're going to build some stuff. We're going to code it up. Okay, so basic concept. So interpretability, I like to think of it as the ability to kind of explain or present what a machine learning model is doing in terms that you can understand. So there's not really like a global definition of interpretability. It's really kind of subjective, and it is kind of like a human concept, like it's whether you understand it. So there's two categories. So one is like the inherently interpretable model. So that could be linear regression. Maybe you have some physics motivated machine learning model. You could have decision trees like random forests. And then you can have symbolic regression. So I'll talk about these techniques a bit later. The post hoc explanations. So that's, you generate explanations of black box models. So the two main ones are Lime and Shapley values. And then I'm also going to talk about symbolic distillation, which I think is good for physics. So transparent models, there's a lot of different kind of standard approaches. So linear regression is the common one. Kernel methods. So this is where the kind of physics in the model is described by the correlation between points rather than in the actual functional form of the forward model. Physics-based neural networks, decision trees, again, symbolic regression. So post hoc methods. So these are, like, again, you want to understand a black box model. Typically, the way industry approaches kind of deal with this is they look at the importance of different features. So if I have a model on that classifies images, I might look at where in the image is most important. So maybe it's like the face of a dog is kind of, I don't know, or that maybe the color of an animal tells you something about it, more than like the background scenery. So the two common ones are Lime. So this is, you basically build a linear model that locally approximates the model and get interpretations from that. And the other one is Shapley values. And I'll give more detail on that later. Distillation is another strategy. So this is where you have a black box model and you want to essentially translate it into an interpretable model. So the technique I like is symbolic distillation. This is where you try to find an equation that is similar to the neural network, for example. So you can kind of think of this as like a Taylor expansion of a neural network. So the trade-offs of these different approaches, like the trade-off of a deep neural network versus, say, learning an equation, is nicely summarized by the following figure from Jay Wadakar's paper. So the symbolic regression is red, deep learning is green, and then decision trees are blue. Basically, what you see here is the minimum. So this is like the model is bad at this, and then the outer circle is maximum. So the model is very good at this. So we see that symbolic regression has very good generalization for physics problems, very good interpretability, but it's not expressive, and it's not great at high dimensional problems. Like you can't really solve image classification with symbolic regression. It's also slow, whereas deep learning, very expressive, good at high dimensional problems, kind of slow at training, but not too bad, but bad generalization for physics problems and bad interpretability. And then we see decision trees as well, which is kind of like in the middle of both. And by the way, so I don't know if I can hear people ask questions, but feel free to interrupt me at any moment. I like interactive lectures. I don't know how I can see the chat, or I don't know if people just want to, like, I think I can hear, maybe, I don't know. Guess we'll find out.
I'm monitoring the room, so if there's someone raising his hand, I'll let you know.
Oh yeah, okay, thanks. Okay, so transparent models. Let's look at the inherently interpretable models first. Again, the goal is to, from scratch, build a model that is already interpretable, but still kind of flexible enough to fit the data. So like in some ways, this is kind of like a controversial opinion, but in some ways, like a lot of astrophysical models, like even the physics models are kind of like this. They're kind of like interpretable machine learning models because you're fitting parameters, right? So it's kind of like, it's rather than just binary, inherently interpretable, not interpretable, it's kind of like a spectrum. The physics models where you have some unknown parameters, kind of like the most, I guess, interpretable, and then at the other end is say like deep neural networks. So linear regression, I'm not going to talk about that. It's just linear combination of inputs, and you can understand the contributions of different features. Decision trees. So a decision tree, I don't know if maybe you have seen this in the other lectures, but essentially you make a classification decision, for example, based on a series of branches. So you can kind of think of this like an if statement in programming, but the if statement conditions are learned, and they're essentially, is this feature greater than this number? Then go this way. If it's less than this number, go this way, until you get to the nodes of the decision tree where you make some kind of classification. So the reason this is interpretable is because you can kind of follow the path down and see, okay, like weight seems to have, so this diagram is like understanding the risks of a heart attack. Basically, you see age. So if I go to young age, then I look at the weight. High weight is high risk, low weight is low risk. So it's kind of like interpretability from that. I mean, it's not too flexible. That's the problem. So there's kind of mixed benefits of these. So symbolic regression, this is what I really like, and I think it's really nice for physics. So the idea behind symbolic regression is that you want to find an equation that describes your data rather than fitting parameters in a fixed model. The reason I like this is because we already know equations are very good at describing our universe. Like this combination of different operators, right? Like plus, minus, multiplication, division. You can describe huge amounts of physics with that. And I think that's kind of like, because the operators are motivated from geometry, like multiplication is like going from length to area to volume. So it's kind of like a functional prior over the space of models. And I think that's why this approach is not only very good at describing our universe, but it's also pretty interpretable. So this is interpretable because it's a language we are familiar with. Like if you have a model described as an equation, you can instantly kind of see connections with existing models because it's the same language. So it was popularized by John Koza in the 1990s. Hod Lipson's group did more in the early 2000s. The idea is you want to find an analytic expression to, say, fit some data set. So here's a view of kind of like how this actually works. So say that this is our data. So this orange line is the thing we want to fit. The current prediction of our model is the black line. Now, the equation is typically represented as a tree in these symbolic regression algorithms. So you see this x plus y tree. So the way these algorithms work is by manipulating this tree until it fits the data. And that's essentially how you search over the space of symbolic regression expressions, sorry. So you see here, maybe we have some mutation to the tree and we add a node, right? So we've gone from x plus y to x plus cosine of y. And so that's one mutation that we could do. So maybe we search over other mutations. Okay, let's add another node. Now the cos becomes cos of y plus 1.5. And we see, okay, maybe it's getting closer to fit the data. So we kind of rate that direction highly. It's kind of like you're simulating the evolution of an equation where this tree is kind of like the genetic code of an equation. We search some more, maybe we mutate. So now we've gone from cosine to sine. Maybe we mutate the constant and kind of like tune the constant a bit. You see, we tune it. And then maybe we add another node and then tune it again. So let's watch this again because it was so time consuming to build this. So let's watch it again. So we add a node. And I mean, the point of this is just, it's a way to search the space of symbolic expressions rather than having a fixed equation with parameters that you tune. This adds another dimension to it where you can search over the space of symbols and kind of arrange combinations of symbols. Okay, any questions on this?
Yeah, there are some, let's start. So is this some kind of like genetic algorithm to find this, or how do you evolve to this?
Sorry, could you repeat it?
Is this a genetic algorithm or how do you evolve through steps?
Yeah, so typically you would solve this with a genetic algorithm. Yeah. So those are kind of like mutations in the genetic algorithm to go from one to the next. That's like a mutation on the genetic code.
Okay, thanks. There was another question?
Yeah, basically directly related. So this is also true for choosing the constants. So there, I think you could actually do some form of gradient descent, but I guess probably not be implemented in conjunction with the genetic algorithm.
Oh, gradient descent on which part?
When you choose the constant.
Oh yeah, so that is solved with gradient descent. Yeah. I mean, it depends on the code. Like some codes are not sophisticated enough to kind of do that, but the code I'm describing here is. Yeah, that part was like really painful to code, but it works. Other questions?
I think we're good for now. Thank you.
Okay. So how can you try this? So I'll give a demo on this tomorrow. So the code that I've worked on is called Pycer. That's the Python version, and there's also a Julia version called symbolicregression.jl. It's fully open source symbolic regression code. Before Pycer, the only kind of like fast symbolic regression library you had to pay like thousands of dollars for. This one's free, completely open source. I've really tried to emphasize like ease of use, and I'll show you tomorrow. And it's scalable, so you can use it on a cluster. There's like a Slurm plugin, there's a PBS plugin, and you can scale it to thousands of cores, which is really useful for the genetic algorithm. You can kind of think of it like in the same terms as like evolution. Like if you have a lot of copies of a species, it can kind of maybe evolve faster. I don't know. So the way the actual algorithm works is you have a population of expressions. So maybe I have x to the power of x. I have this 1.15 times y plus another constant x times y cubed. So I have this list of expressions. That is my population. And basically what I do is I randomly subsample from that population. So maybe I pick 2, okay? Of those 2, I run what's called a tournament. So this is a tournament selection style algorithm. So I run a tournament between these 2 expressions. I then select the fittest. So the fitness is something that you would have to assume. So maybe I want to look at the fitness in terms of the mean squared error of the expression with respect to my data. That's the most common one. But you could also think of like other fitness principles, like maybe whether it respects energy conservation or the simplicity of the expression. There's a lot of different things you could put in that fitness. But the point is, once you have that fitness, you pick an equation from the tournament. Then you can do one of several different perturbations. So maybe you have that equation and you mutate it. So you take the y and you make it y squared. Or maybe you take the plus 0.86 and you delete it. Or maybe you do an algebraic simplification, which does nothing here, but you could do that. Or maybe you do an optimization. So that's where you would do the gradient descent. And maybe solve like 3 steps or something simple. You could also do a crossover. So if I have these 2 expressions, maybe I swap the y for the x to the power of x, and I kind of swap it. That's one of the different kind of perturbations you can do. You can kind of cross over 2 expressions. Yeah, and then you basically just loop. So it's pretty simple. There's not like too much I don't know, the algorithm is pretty simple. Like you just want to go through this loop really, really fast with as many examples as possible with a kind of some data set. And this is a way to optimize and find a symbolic expression. I mean, it doesn't scale well with complexity. So if you have a very complex equation, it's hard to find it with this kind of approach, but it is kind of like one of the only things you can do that will generalize to unseen expressions. Yeah, if you have a question, just shout it out because I can't see anybody. So
Yes, there's one more question
question. Is
Okay.
there a reason why you use genetic algorithm instead of, let's say, RNN or VNN or reinforcement learning or any other kind of algorithms? Is there like an intuitive, powerful reason why you use genetic algorithm, or is it not there?
Oh, yeah, that's a great question. So, yeah, I mean, there are some approaches which do involve machine learning, like traditional, well, maybe not traditional, but they involve like reinforcement learning in this loop. So I think if you're pre-training the model, so if you have some random set of equations and you kind of train the model on those, it doesn't generalize well. So there was a competition last year and the pure deep learning approaches got crushed by the genetic algorithms. Like it's something that genetic algorithms are still kind of superior in. I don't know if that'll last, but it's really hard for models that have been trained on a set of equations to generalize to new unseen equations, because the space of possible equations is just massive. Now, one thing you could do is, so some people have this reinforcement learning in the loop. So you kind of have the reinforcement learning pick the mutation or pick the crossover that you do. And that seems something that will generalize much better, because it's like, at worst, it's the genetic algorithm, but at best, it's like this highly tuned RL algorithm, which kind of sees, it's like you have a god watching over a species evolve, maybe, and kind of like picking the right, like the right pathway to go down. Yeah, I mean, genetic algorithms are still the best out there, but I think that approach is promising. It sounds promising. I think the future is kind of like a mix of the two is the best bet. Yeah, but like genetic algorithm, it's really all about performance. Like how fast can you go through this loop? And then you just evaluate as many times as possible. But the algorithm itself is like not very clever. Like you're just going through this loop. Does that answer?
Yeah.
Yes, thanks. There's
Okay.
another
Yeah.
So how you showed this right now, this kind of mutation algorithm doesn't seem very systematic, I would say. How systematic can you really do this?
So yeah, it's not systematic. Basically, what happens is you have a constant set of probabilities for each possible mutation. So one of the mutations is you do an operator swap. One of them is you add an operator or like add a new subtree. One of them is like maybe you delete part of the tree. And those have constant probabilities. And some of them are much rarer than others. So like the optimization happens very rarely because it's so expensive. And those probabilities are just tuned on a large set of equations. It's I mean, it's not like you're tuning neural network parameters. Like those parameters are hyperparameters. But yeah, it's not really systematic. I mean, the only conditional part of the mutation weights is the probability of optimizing the constants is I think it's proportional to the number of constants or something. There's different like conditioning in the algorithm. But that seems like something a neural network would be good at, kind of like picking the probabilities, for example.
Okay.
Yeah, there's one more question.
What does exactly this example age regularization mean?
Oh yeah, okay, good question. I didn't explain that. So the traditional way of doing a tournament selection style evolutionary algorithm like this would be to replace the worst equation in the population. So you have this population of expressions, maybe you have 100 different expressions, you find the worst one and you kill it and you remove it and then you put the new expression in. Age regularized evolution basically says what equation has been in the population the longest, remove that one. And that just prevents it from converging too quickly to like a bad space or a bad spot in equation space. So it regularizes it and it helps it find a better minima after a period. Like it'll take longer, but you'll find a better equation. So it's like replacing the oldest rather than the worst equation.
Okay, thank you.
Okay. Yeah, happy to answer others as well. Okay. So PICER is not just an evolutionary algorithm, it's a multi-population evolutionary algorithm. And what these kind of algorithms do is they, rather than having one population of equations, you actually have many, many different populations, and they each evolve independently. So I like to think of this as like islands. So it's like some set of islands in the ocean, and you have a different kind of like species of equations that evolves independently for like thousands of years on each island. And then once in a while, randomly, there will be a migration between islands. So it's really like a lot of parts of this try to emulate evolution because it seems to work well. And so you'll have this like migration between the islands, and they'll send like their best equations each way, and you get, so if one island is kind of specialized to polynomials, another island to trigonometry, you'll get some new functional forms, and then they can do crossovers and kind of mix in. The practical reason why you would want to do this is it's very good for parallelism, because you can have an island on a core. So if you have thousands of cores, you can have 1,000 different islands kind of evolving on a single core, and then migrate between processes. That's kind of the practical reason. But it does help, it helps you find better expressions because you don't have as much like early convergence to bad minima, like converging to a good expression, but not kind of like having good diversity of different equations. Yeah. Okay. Okay, so I'll go through some. So that's symbolic regression. That's one possible way of kind of putting in priors to the model, so you get an interpretable model out. Another way to do this is by having, so say you have a neural network, and you want to kind of make the neural network look like the physics you already know. So this is where you get into what's called an inductive bias. So I'll talk about energy ones, geometry ones, and differential equation ones. So there's this thing called the curse of dimensionality. Basically, in high dimensional spaces, it's very hard to optimize because essentially there's just so many directions you can take. So inductive biases very abstractly define a prior over the space of what functions can be learned. So you could think of this as what possible equations are there, and then the subset is what possible equations are there that conserve energy, right? So that is an inductive bias. But an inductive bias in the deep learning sense is kind of, it's a way you write your deep learning model such that it respects some prior, basically. So an example is like, if you're training your neural network, what you can do is you can penalize the network based on the squared sum of the network parameters, for example. So this is called weight decay. This is an inductive bias because it limits the network to learn smooth functions, because it can't really have like some parameters be massive and some parameters be small. It kind of needs to have everything kind of close to zero. But a physically motivated inductive bias is like, the inductive bias comes from physics. Okay, so one approach to doing this is called an energy-based model. So one example is like kind of like diffusion models. So it's from statistical physics. So the formalism all comes from StatMech. Basically, the network tries to predict the energy between two data points. And you want to maximize energy over negative pairs of data and minimize energy over positive pairs of data. So let me show you a diagram. So this is my model. So it could be like a neural network, for example. It takes in two inputs. One is an image and one is text. Okay. And if they are positive pairs, so like if they match, so like Einstein's, a picture of Einstein and the word Einstein, you would try to minimize the energy of that. If they're completely separate, you would try to maximize energy. And so this is actually, it's kind of like a formalism for thinking about models in machine learning, but it's actually like very close to physics, and you can think about like actually using this for physics problems. So many different machine learning models can kind of be phrased in this framework. And I think the nice thing is for the physicist is because you're learning this kind of concept of energy, you can actually interpret it. So I'll show you, you can actually interpret this as like a literal energy for certain problems. So there's this really cool idea called the Hamiltonian neural network. So it's from Sam Gradenis in 2019. Essentially, you have this type of model where you predict the energy.
Here, sorry.
Yeah.
for the question.
It's something to be a slide.
Sorry?
So
On the previous slide.
Oh, yeah.
yeah, so I've heard the term conductive learning before. It's like, and it sounds to me that it's very similar to this. Can you explain the difference?
In inductive learning.
Contrastive learning.
Oh, contrastive learning. Yeah. I mean, so energy-based models are kind of like a formalization of contrastive learning. Basically, it's like taking contrastive learning and putting it in a statistical physics framework to kind of exploit the different properties you can get from that. But so contrastive learning is a kind of subset of energy-based models. Yeah, and it's used like in so many different applications. So like a great example is like generative pre-training. So like stable diffusion, for example, uses this idea. Yeah.
Okay, thanks.
Cool. So Hamiltonian neural networks take this even further. So they not only learn an energy, but they also apply Hamilton's equations during the prediction step. So you predict H, so your network takes in two vectors, right? One for momenta and one for position, predicts one number, which is the energy. Now, you don't have the energies. What you do have is the acceleration. And so what you do is, actually, let me show, okay, so what you do is you use Hamilton's equations, and basically you take the derivative of your network with respect to the inputs, which gives you Q dot and P dot. Then you fit Q dot and P dot against your data. Okay, so like if you have some simulation of a ball falling, right, you would get the acceleration, which you would put in P dot, and the velocity for Q dot, and then you try to make these equal. So you try to make the gradients of your network equal to the dynamics. Whereas normally you would try to make the predictions of the network equal to the dynamics. Here you're making the gradients of the network equal to the dynamics. And that lets you use this approach, which is Hamilton's equation. And basically that gives you energy conservation. So you can even apply it to like a latent representation in a video, which is really cool. So you see like the normal neural network doesn't know about energy conservation. So it kind of like takes the simple approach and just diffuses energy because that's maybe like a safer assumption. But the Hamiltonian neural network can't because you're solving Hamilton's equations. So I had this work with Sam and others that followed this up with a Lagrangian neural network. The issue with Hamiltonian neural networks is they require you to know the kinetic energy to actually get the canonical momenta. So what this does is you just take the Euler-Lagrange equation, rearrange it, and you get this Q double dot term. So all you need is the position, the velocity, so the time derivative of the positions rather than a canonical momenta. And that gives you, you also get conservation of energy from that, but it's like less assumptions, but you still get energy conservation. The issue with this is it's kind of ugly to solve it. Like you have to do like a matrix inverse. It's kind of nasty. But it is, so these two approaches are, I would argue, more interpretable than a regular network, because now you're learning an energy of the system rather than a time stepping model. Like you're not learning, okay, what's the next time step? What's the next time step? Which could be very complex depending on the system. Now you're learning an energy. So you can compare that to like what you understand about the energy of the system. Questions on this?
There's a question.
Yeah. So why exactly do Hamilton neural networks require the functional form of kinetic energy?
Why do they require what?
The functional form of kinetic energy.
Oh, so to get the canonical momenta from the velocity, because they're not equal, you need to know the kinetic energy. So oftentimes, like if it's classical, you can just like learn the masses in the system. But if it's not classical and you have like a weird kinetic energy, or if it's like a magnetic field or something, you can't use a Hamiltonian neural network without assuming the kinetic energy, basically. So this is like, if you just have position velocity, but yeah, but like most of the time you can use a Hamiltonian neural network and it's like more stable to train, etc.
Yeah, but this is because of the differentiation or automatically, right?
Sorry, say it again.
Yeah, so you mean this is because of that you have to differentiate to get your Q, or you get the Q dot?
So it's because you need to know the canonical momenta of the system to give it to the Hamiltonian neural network. If you set this P equal to Q dot, for example, then it doesn't, like it can't learn it will just like give like a constant solution or something. So it has to be the canonical momenta of the system, and to get the canonical momenta, you have to assume some form of kinetic energy. The Lagrangian neural network, because you solve it with the Euler-Lagrange equation, you don't need that. It's just all in the Lagrangian. The bad part is like you have to do all this other gradient stuff, which are kind of like you're computing a learned canonical momenta in a way.
Yeah, no, I'm kind of asking because we actually had a lecture on this before, and I think.
Oh, okay, cool.
And you actually kind of learn the momentum.
Yeah, so you can do that. So you can also learn momentum. The problem is you lose you weaken the energy conserving property, because now you have this like larger manifold that the space can explore. So you can do that, and actually, so that's what this is. So this video here, like this canonical momenta is learned from the video. The downside is like it's not 100% energy conserving, because it could learn some kind of like weird canonical momenta that diffuses energy, for example. But yeah, both of these approaches, like they require you to, like they assume that, okay, you've learned the correct energy, but like it should kind of wrap around in phase space anyways, even if it's incorrect, which is good.
There's another question.
So you can model energy law with this, did I get this correctly? Then
So can you model energy loss with this?
Can you model energy?
Energy loss with this?
Oh, there's a follow-up paper on this. The basic idea is that, so like this by itself does not model energy loss. What you have to do is you add a term that accounts for external forces. And you have to regularize that to be small. And that is essentially the energy loss term. But you lose the energy conservation, which is like the main reason you would use this. I mean, it is nice to kind of like disentangle them. So now you have an energy and you have a diffusion term, which could be nice.
Okay.
And then the Lagrangian, I think, what is it? I think you just like add a term here for the external forces, and then you would rederive this equation, maybe. But again, you would have this like, you'd have to regularize it to be small. Otherwise, it would just lose the energy conserving principle. But yeah, good question. Yeah. Okay.
Okay.
Yeah, so this is an example of, I think this is like special relativity. So if you're modeling a particle in special relativity and you just give the velocity of the particle as the canonical momenta, the H and N just can't learn it. It's just like the manifold of models it can learn is just does not contain the true dynamics in that system. So like maybe you could also learn the momenta here, but you would lose the kind of hard constraint basically. But you would also get like the benefits of a Hamiltonian neural network, which is like a more stable training. Yeah, okay. There's one other approach. So this cool idea called Hamiltonian generative networks. Basically, you define the probability related to the exponential of the energy and the negative energy, so from StatMech, and then you try to conserve the total probability. So, right, like, so rather than conserving the energy, conserving the probability. And the advantage of this is you can work with normalized distributions. So you could use this for kind of statistical inference, maybe, and you would get conserved distributions. So like the integral of the distribution will be constant. So they implemented this for this idea called the normalizing flow. I don't know if people have heard of that before. Like maybe there's a lecture on that, but the basic idea is you learn probability distributions. I don't know if people use this. Like I think like a standard normalizing flow is still the most popular approach, but it is a cool idea. Yeah. Okay. So one other kind of inductive bias that you can impose is with a specific geometry. So we've talked about like energy this far, but you can also impose like specific geometries on your models. So convolutional neural networks, like shown here, right? They are translationally equivariant. So like you translate the image, you'll also get a translated latent space. And yeah, I won't go through all of this, but the basic idea is like this is kind of like momentum conservation. So there was this nice paper from Max Welling's group that generalized this idea, and they made this model called the group equivariant CNN, and it makes the CNN rotationally equivariant as well. So, or I think it's invariant, sorry. So rather than just like having this translation ability, you can also rotate an image and the CNN will predict a constant output. So yeah, I won't go through all of this, but the basic idea is you would have some symmetry group. So that is G. And so, okay, so actually maybe I will discuss this. So this top approach is a convolutional neural network. So we have some image F and then a convolutional filter psi. And we essentially convolve the filter. So that's what this X minus Y is. Like you're convolving it over the image. Now they looked at this and said, okay, X minus Y is the inverse of some group, some symmetry group. So they said, okay, just write that as like the inverse of some group operator. And so they actually make this a discrete group, but I think they generalized it and made it a continuous group. But once you write it in this formalism, you can just write down like a rotation operator for G, and then you get these rotationally equivariant filters, which is a cool idea. And so the way this relates to interpretability in physics is that like it's just I think these different geometries are good to impose so that the thing your network is learning already respects the symmetries that you know. So when you do kind of inspect it and try to understand what it's doing, you don't have to see like, okay, it's learning symmetries here, like it's just already imposed. So you can worry about the other parts. Yeah, so I won't discuss it too much more, but there's this other cool idea called a graph neural network. I don't know if anybody's reviewed this yet, but essentially it also gives you permutation symmetry. So now you get like, you can get translational, rotational, and permutation symmetry. And there's so many papers on symmetries now. There's like Lie symmetries, Clifford algebras, there's crazy things. But yeah, I think generally what I'm trying to say is that it's a good idea to impose symmetries you know already like exist for your problem, because then the network doesn't have to learn that. So the interpretation of the network is easier at the end. Questions yet? Okay. Oh yeah, I'll shout out this book. This is a nice book. It's called geometricdeeplearning.com. It's this really nice book on different ideas in geometry. So if you're interested in those two topics, I would check it out. Okay. So the one other idea I'll discuss in inherently interpretable networks is differential equations. So a lot of ideas in deep learning are basically assume discrete sequences with kind of like evenly sampled times. So like the long short-term memory network, the LSTM, which is a type of RNN, that was, I think it was originally designed for like financial data, which is of course evenly spaced. But in the sciences, we don't usually have that. We have like unevenly sampled time series. And we also have like continuous dynamics happening. We don't have like discrete jumps, right? We actually have continuous dynamics in the system. So the general idea behind this is called a neural differential equation. Stop me if this has already been introduced, and I can skip it. But if not, I can talk about it. So the basic idea is that your network, rather than learning to predict the next step, it learns the acceleration, or it learns the velocity of a variable. And then you can integrate basically the output of your network with respect to time and get some future prediction at a continuous time, because you're literally like solving an integral with an adaptive integrator, where the velocity is given by a neural network. So this lets you model continuous dynamical sequences and train on unevenly sampled data. So the idea, so this is an old idea, but the contribution of this paper was like to point out, okay, a lot of neural networks kind of do this already, but they have like discrete jumps. So why not solve it continuously with an adaptive integrator? And then you can get like an arbitrary time sample rather than just like on a discrete output. So this is another idea that can help you interpret a network. If you kind of like solve it as a differential equation, then you can interpret the network as like a velocity rather than just like a forward step. So again, it relates to the Hamiltonian neural network, Lagrangian neural network, the idea of predicting like an energy, which you would then get a velocity out of, that sort of thing, or acceleration out of. Okay, so so there's this other idea called a physics-informed neural network. The name is kind of a misnomer because it's like, you could think of like physics-informed neural network as like any neural network with physics, but it's actually, so PIN, P-I-N-N, is like a very specific approach. I don't really recommend these in practice. I think they're very good and interesting idea, but they're not yet proven for like complex systems. The basic idea is that your neural network goes from position and velocity to some variable. So like if you're solving the wave equation, you would have a neural network take a position in time and predict the instantaneous velocity at that point. Then what you do is your loss is the differential equation. So you would take gradients of the network with respect to the inputs, and that is like the gradients of a velocity field. You then optimize that PDE, and that basically gives you the solution in like represented in your neural network. So unlike the Lagrangian neural network and the Hamiltonian neural network, this is a soft inductive bias. So if you have like real world data, you can kind of like softly push it to the right equation, but not force it, which is a good idea. The reason I don't recommend it in practice is because it's really hard to train them. And I think they haven't really been proven for complex PDEs. Yeah, any questions? Okay, yeah, and so one thing to keep in mind is like, this is you're learning the solution, you're not learning the dynamics. That's kind of the difference between a pin and like a Hamiltonian neural net, for example. So you can't really take the same pin and apply it to a different problem. You have to retrain it on each data set. Okay, so I'll just make some classifications here, which I think are useful for thinking about inductive biases. So I would say that a soft inductive bias basically says that it is difficult for a model to deviate from like some prior over models, but it's not impossible. Now a hard inductive bias is like, it is impossible for the model to not respect inductive bias. So like a Hamiltonian neural network, it's impossible for the model to lose energy. Like it's just written into the architecture, it cannot lose energy because you're literally solving the Hamiltonian equations. I mean, it could have the wrong energy, but it's going to conserve the energy it learned, basically. So a CNN cannot learn like absolute positions because it literally doesn't know the absolute positions. It just sees like relative positions, basically. So another angle of this is like explicit versus implicit inductive biases. So an explicit inductive bias is like you have a specific functional prior in mind. And an implicit is like, it's present in the model, but it might not have been intended. It's kind of, it's hidden in how you've set up the model. So for example, when you train a neural network, you just like take a random neural network, you initialize it and you train it. You actually have an implicit regularization that the network is smooth. And that is a prior that you haven't really like explicitly put there, but it is present in the model. Whereas the explicit biases that I've talked about are kind of like, you know, the physics respects energy conservation, so you put that in. So I think, yeah, I'll just skip through this a bit. Let me skip this. Okay, let's talk about post-hoc methods. So what we've talked about so far is inherently interpretable methods, but we haven't talked about, okay, like I've already trained this massive neural network. How do I understand what it's doing? This is a post-hoc interpretability method. So we've used some black box neural network as it was more flexible. Now we want to understand what it's doing. So there's two ways to go about this. One is looking at the feature importances and trying to understand what's going on from that. So the two common approaches are Lime and Shapley values. You can also distill a network. So this is where you take a network and you try to translate it into a simpler model that you can understand. So like symbolic distillation, I'll talk about a bit. This is like, you try to find an equation that looks like your neural network. So the general idea about feature importances is that you try to look at what the network is most sensitive to. This sometimes it's called a saliency map. A saliency map is roughly equal to the gradient of a function with respect to the inputs. Okay, so like if I have a classifier, a neural network classifier that's looking at an image of some lions, and I take the gradient of the classification with respect to the image, I get this heat map of basically what the network is looking at. So maybe it looks at their faces or something. And this dog, like it's not looking at the background, it's looking at the animal. And that's a saliency map. Now, two other ways of going about this, which are a bit more rigorous. One is called LIME. This stands for Local Interpretable Model Agnostic Explanations. The basic idea is that if you want to understand the predictions of your model at some point, like you have some input and you want to understand, okay, like why did my network predict this value? LIME says, okay, fit a linear model around that point. Find a linear model that approximates that point and then look at the linear model and try to get interpretations from that. So you can do this even with high dimensional models. So like here's an image of a dog playing a guitar, and they have different classes. So like electric guitar, acoustic guitar, and then Labrador. And so if the model looks at this image and it predicts like electric guitar, they fit a linear model to it. And basically what they find is that these pixels, so they're literally looking at like a linear model with respect to the pixels, okay? And then they get this map that basically shows what the model is looking at. And you can do like acoustic guitar and it looks at like the wooden, the brighter colored parts, and then Labrador, it looks at the face. So I think this is a nice idea for like interpreting very complex models and getting like a quick interpretation out. Any questions? Okay. Another idea is called Shapley values. This is, so it's another approach to getting feature importances. It's based on game theory. It deals with cooperation of partners. So if I consider 3 people A, B, and C, if I consider them by themselves, maybe A contributes like 1 point, B by themselves contributes 2 points, C by themselves contributes 3 points. And then I look at their combination. And now, because this is about cooperation of individuals, it's not just the sum of their individual contributions. They actually get, because they cooperate, they get more points. So I could see this is like 6 points if I combine A and B. If I combine B and C, it's like 5 points. And then A and C, I get, what is that? 6.5 points. And then I combine all of them and I get this many points. The Shapley value is I think it's like the integrated contribution of one person over all possible permutations and like combinations of people. Yeah, combinations, not permutations. So that is the Shapley value. Now, that is another way of thinking about feature importances. So like if I have a tabular data set and I want to know, okay, like what is the most important feature? Basically, you retrain your model from scratch on every possible combination of features. And then you can look at the Shapley values. And that can tell you, okay, like this combination of features is this important. This feature over all combinations is this important, and so on. So there's this GitHub package called Shap, which kind of does this automatically for you. It's nice. Yeah. Any questions? Okay. Okay. So now we'll get into the distillation part. So science has a modeling language, right? Like we don't need to just look at which physical variable is important. I mean, like sometimes that's useful, but we actually have a language for describing models in science. That is like, so computer vision, maybe you don't have like a model for a cat, right? But in science, we have equations. Like we have a pretty good understanding of our data already, and that is with mathematics. So what, like the problem here is that, so if you look at the history of science, okay, like a lot of the time, there's been some empirical observation and then theory to kind of derive that observation. So like Kepler's third law came like what, like 80 years before Newton's law of gravity, but it was, Newton's law of gravitation was created to explain Kepler's third law. Planck's law was actually, like a lot of people don't know this, this was an empirical equation first. Then quantum mechanics was partially kind of created to explain this and other phenomena. But neural networks, like if we have some huge black box model, like we don't really get anything from that. Like we can't build theory to describe the neural network weights. I mean, like we could look at the feature importances, but like, I don't know, like if you look at the feature importances of like Kepler's third law, it doesn't really give you anything to aim for in theory space. Like you can't really build theory to derive feature importances. And that's what I see as like a problem of these traditional post hoc explanation approaches. So like the language of mathematics is very good for us. And so I think it makes more sense to distill concepts in that language. So that's where I go into the symbolic regression. I'll show this video for like the 5th time or whatever, because I spent so much time on it. Yeah, look how cool it is. Yeah, so let me skip this. Oh yeah, this is all the same slides. So can we combine symbolic regression and deep learning? That's the idea. So rather than using symbolic regression directly on the data, what you could instead think of is using symbolic regression on a neural network. Okay, you have the black box model, use symbolic regression to understand what the network is doing. So we introduced the idea in 2019, 2020, where we kind of convert different networks. So we have like a graph neural network and we convert it into an equation, and you actually rediscover the laws that you put in. And we found this new equation to kind of empirically describe like the clustering of dark matter. And this is something like, I don't think we ever really got that much insight from this, aside from like heavy things are more clumpy. But the point is like, we couldn't have done that. We couldn't have even like thought about that without distilling it to an equation. So I think it's a useful technique. Okay, the way it works is if I have a neural network, right? And it goes from 4 inputs, like x1, x2, x3, x4, to 2 outputs, y1 and y2. Symbolic distillation converts this into my language, which is symbolic regression or symbolic expressions. So I want to find equations that approximate this input-output relationship. Okay, so I'm kind of treating the neural network as like a data generating process that I'm trying to get equations for. Any questions? I want to make sure this makes sense. Okay. So it's kind of like you're doing a Taylor expansion of the network, right? Like we do Taylor expansion of models that we don't really understand that well, right? We do a Taylor expansion, and then you kind of work through it and try to understand like the first order dynamics. It's kind of like that. Like you're trying to get equations that fit the neural network rather than just letting it be a black box. So the idea is that you would train a neural network normally. Okay, you just have some neural network that's already trained. Then you study it. You kind of watch the neural network. You see what are the inputs, what are the outputs, and you record a data set of like input outputs of the neural network. Then what you do is you feed those into PySer, and PySer will say, these equations are how you can best approximate this. Like these equations are good for modeling the input-output relationship. Okay. Questions? Okay. So one thing you might ask is like, okay, but Miles, like why not just fit symbolic regression directly on the data? Sorry. Yeah.
There's a question.
I think
Yeah.
start there you go.
Okay, it
Oh,
might
okay.
be. Oh, okay.
I was like saying what you were saying. Yeah. So like, okay, Miles, like why not just fit directly on the data? Like why have the neural network at all? Like just fit on the data. So the point of symbolic distillation is not so much to like just for simple networks. It's really for more complex networks where you have a hierarchy of different models and you understand a tiny piece of it, and maybe you understand like multiple pieces of it and kind of stitch them together. Because if you were to do symbolic regression directly, like the final equation is maybe massive, and it's not really possible to find that directly with PySer. So the neural network here, it's kind of like it's factoring it into smaller problems that are solvable with PySer. So say I have some network of 2 parts, like F and G, and maybe I interpret like, okay, maybe the first network is kind of like learning some, I don't know, like maybe it's learning the Christoffel symbols, and then the second network is like doing something with those. So like the first network, maybe it's learning features, second network using those features for something else. What you would do is you would first fit the network F. You maybe find some equations for that, right? So we've interpreted the first network. Then you've replaced the first network with those equations. Okay, like you rip it out, you put your equations in, and you can do the same thing with G, right? And then you get this hierarchy of equations. But actually, so what we do in practice is you would retrain the second network, because typically the first network is not going to be perfectly approximated by the equation. So this kind of helps you pick up any errors in the approximation. So you retrain the other networks, and then you get an equation out for those. Now you have this hierarchy of symbolic interpretable models. And I think like, not only is it important that your entire model is symbolic, but actually this hierarchy, I think, helps you interpret even better, right? Like you could think of this as like summary statistics, and this is like doing something with the summary statistics. So it's actually nice to have this hierarchy of equations. But this is what the fully expanded form would look like. This is doable with PySer to find this equation. But like for much more complex things, it's hard to get an equation out, like just by searching directly.
I have a question.
Yeah.
So if you repeat this process, you would get like different sets of equations, which would be like totally uncorrelated, right?
Oh, you mean like if you retrain the network from scratch?
Yeah, exactly.
Yeah. So yeah, great point. So there's a degeneracy here, as you correctly pointed out. So shit, I think I deleted that slide. So the degeneracy here is that whatever F learns, like G can just inverse that and then do something else, right? So actually, even though I wrote it like this, typically what you would have is these latent spaces would have some other thing going on that would kind of split the network in a sensible way. So like maybe this first network is like per particle, and then it does like a per particle, maybe it does like a coordinate transform of each particle. Then I do a sum in that latent space. Maybe I sum over all the particles, and then G would map from that sum to something else. And that's how you break the degeneracy. There's like a couple other degeneracies, but you can kind of dampen those down with different regularization. So like sparsity is good, L2 regularization is good, and that kind of breaks down the degeneracy a bit. Yeah. But yeah, that is like something that's like it's difficult to deal with. That's like the trickiest part about this. Yeah. Okay. So yeah, so the point is like with symbolic regression directly, if we consider n equations for F and n equations for G, normally that would be n squared equations that we'd have to consider, roughly. And now we only have to search over 2 times n equations. I mean, like, okay, it might be a bit more inaccurate, but it's a much smaller search space. Okay, I'll just show 2 quick examples. So this was a recent paper by this grad student at Wisconsin, Ho-Fung Choi, and basically he used PySer not for interpretability, but for getting a expression on an FPGA. So this is, I think this is like to put on the FPGAs for anomaly detection at CERN or something. Like I don't understand I don't really understand the application of it, but basically they had these neural networks that were trained to do anomaly detection at the LHC. But the neural networks are too slow. So they distilled those networks into this like really condensed equation that they could put on an FPGA, and it's like much, much faster. So that's like, it's not interpretability, but it's another thing you could do with this, is kind of like distill it to a faster version with some approximation error. And so they got like pretty good inference time. So one other example, I'll just quickly go through this. So this is led by Pablo Lemos, who's now at Montreal. This paper considered, can we learn orbital mechanics? So like, can we learn Newton's law of gravity just from the dynamics of the solar system? Okay, so just by watching how the planets move, can we find Newton's law of gravity? Like, no, we don't know the masses, okay? Like, that's the really tricky part. We don't know the masses of the planets, We don't know what dynamical model there is. Can we find both? And so like, obviously this is a known law, but I think like, if you can't rediscover known laws, you definitely can't discover new laws. So I think it's a good test case. So I'll just quickly say like, actually, okay, so this is the problem setup. We know the position of each planet at some time. We know the acceleration of each planet at some time. We don't know the masses of each planet. I just wrote that as new here. That's like the mass variable. And we don't know the force law, okay? So we got to learn the masses and the force law simultaneously. Okay, so this is the loss function. This is the thing we're trying to optimize. We're saying that we have these known accelerations of the planets, just like we're just doing, looking at the change in velocity, right? Like we want to predict those accelerations based on some learned force law summed over the planets. Like all bodies in the system, the sun, the planets, other moons. And that force law gets the displacement between the two bodies and the two mass parameters. Okay. So the only thing we're assuming here is we're assuming like it's a sum of forces, which I think is fair because like you can get that from terrestrial dynamics. And we're also assuming, so Newton's laws of motion, and we're assuming translational equivariance. So like you translate the whole system, the force laws shouldn't change. Okay, we don't know the force law, we don't know the parameters. We want to learn both the force law and the mass parameters simultaneously. Okay. Any questions? I should ask that first. Questions? Okay. So we give it 31 bodies. So the sun, the planets, and a bunch of moons. 30 years of training data, and then 3 years of validation. So this is another video that I spent like way too long on, and I should have done other things, but I did it, so you can watch it. This is the predictions from this neural network. It's a neural network that predicts the force laws, and then we integrate the dynamics. So this is some of the planets in the system. And the predictions are the wireframes. You can see like, it's okay. Like it doesn't blow up, right? But it's not that great. So Mercury is like really bad. So now that we have this interpretation strategy, we can think about, okay, like now we can figure out what's going on with the network. So we approximate the input output of F, which is the learned force law, with symbolic regression. Okay, so we stick it into PySer. Now, PySer will give you the best expression at each complexity. Complexity is the number of operators, variables, and constants. You can redefine it if you want, but that's just like, we just did that simple assumption. So what I'm showing here is the best expression at each complexity. The y-axis is this score that people use. It's kind of like the trade-off of accuracy to complexity. So you can see like the red one here is x divided by r. Then we go to x divided by r plus a constant, x divided by r times r plus a constant. So it's kind of getting closer. We have constant and then mass times x over r squared. So that's getting there. And then finally we have, so this is Newton's law of gravity, constant times mass times x over r cubed. So this is like the best fit at complexity 13 to the network's input output. There actually was one other model that did better, which was Newton's law of gravity plus a constant. And I think that was just, I mean, like, look at the trade-off, like you can't even see the bar. So I'm assuming that was just like, basically like noise. But the point is that we've kind of verified the network has learned the thing we expect. And it's learned these just from the dynamics itself. So then what we do is we take that equation, we put it back in. So we rip out the neural network, put the equation in. I mean, it is like Newton's law, so you would expect it would work, right? And it does better, but still not perfect. So you see, like, yeah, the bodies are kind of offset, right? It's not completely good. So okay, so we went back to the drawing board. Like, okay, what's going on with this network? It's learned Newton's law, right? And it seems to learn the dynamics okay. So what's the missing piece? So we looked at the learned mass parameters here. So the truth is the blue, the predictions are in red. The different dots are basically different times we ran this experiment. And what you can see is that like many of the predictions are bad, like they're really bad. It's like Mercury is way underestimated. The moons are all over the place. So what we realized is like this network, like because neural networks are so flexible and we only have 31 examples, it's kind of like learned a modified theory of gravity that works for our solar system with its like weird learned masses, but like obviously it wouldn't work elsewhere. And it's not like it does perfectly. So, but like it did find the right law of gravity, right? So what we think happened is that it's just like learned some second order correction terms to account for its weird learned masses. So then what we thought is, okay, this symbolic distillation idea, you're supposed to fit the network and then you fit the other parts of the model. So that's what we did. So we fit the masses after putting the equation in. And I mean, this is like, it's kind of like cheating. Like, I mean, because we can already see the masses, but I think this is generally a good idea. Like you want to refit the other parts of your model after replacing a neural network with an equation. So we do that, re-optimize the masses, and then we do it again, and then we get like a good result. So now it looks good. I mean, like obviously it's not like a new thing, right? Like it's just solar system dynamics. I mean, but it is cool that this pipeline is kind of completely automated. I mean, it wasn't really like we had to look at it, but the idea is kind of applicable elsewhere, I think. So there's like different ongoing works that have discovered like new kind of empirical laws from this. Yeah, the point is like this is it seems like a good idea to kind of distill models with symbolic regression. Because you can get equations, you can understand what's going on, maybe you can make a new discovery with it. Yeah, and so the masses are all pretty good. There's some that are off, like Hyperion and Phoebe are off, and we realize like that's just the gravitational influence of those bodies is so low, you can't infer them anyways. So it's like, it doesn't even matter. Yeah, so the FAQ is like, okay, why not fit directly? So generally neural networks, because you can train a neural network with a gradient, they only require like 1 million gradient steps to train. Genetic algorithms are super inefficient. They require like 1 billion, 10 billion evaluations to find the correct expression. So
Here's a question.
Yeah.
So you said that the gravitational influence of like these 2 or 3 moons is too low to actually.
Yeah.
So you plot, I think, like multiple points for each moon. So is this like uncertainty or what is?
Yeah, it's like yeah, I mean, we basically just reran the whole experiment, and each green dot is a different experiment. So it's kind of like the uncertainty there.
Yeah, but if you say the influence is too low, then we don't infer the right value, but shouldn't the uncertainties capture the true values anyway?
Yeah, that's a good point. I think it's like, I mean, it's partly because you're fitting in log space, so things are a bit weird. I mean, it's also because we've kind of only included 31 bodies. Like we did a mass cut on the moons. So it could be that part of those masses are like accounting for the other moons. But yeah, it is true. Like you would hopefully expect it to cover the ground truth. So yeah, it is weird that it didn't.
There's another question. Like, I think you have some kind of domain knowledge on what went wrong, and that's why you look into Mars, right? So is there like a problem independent matrix to kind of check what went wrong in the problem? Like, you know, like here you know Mars went wrong, right? In a different problem, you might not be that straightforward. Is there like an independent matrix to check this?
Yeah, so I think the best way to check is try on the test set, the validation set, and just see like, is it a good fit? And that is like general, like it's not just here. You could see like, okay, with these assumptions, is it a good fit? And you just have to jointly optimize for simplicity of the model and accuracy of the fit. And I think if you don't get good fit, you don't get good generalization, that indicates that something is wrong. Whereas here, like we know exactly which part is not working. But I would also say like, okay, generally it's a good idea to always refit each part of the model after you replace one of the neural networks. I think that is like a general principle to use in other problems where you may not know the truth. Does that answer?
Thank you.
Okay. Yeah, so why not fit directly? Like neural networks are just more efficient to train because they can use gradients. Genetic algorithms cannot use gradients. So that's why like fitting symbolic regression to the neural network is actually more efficient. Let's skip this. Okay. So in summary, I talked about the basic concepts of interpretable machine learning. We talked about inherently interpretable models. I'm going to put all the slides on the Indico if you want to read more about them. The postdoc method, so I talked about Shapley, Lime, symbolic distillation, which I think is really good for physics. And then we discussed a couple examples. Yeah, so tomorrow we're going to build things. Today was like the slides. Tomorrow we're going to build stuff. Again, I'm sorry I couldn't be there in person. I really wanted to. Yeah, I'm happy to take questions. Yeah, thanks.
Thank you.
Yeah, maybe one question. So, I mean, you said it a couple of times that formulas are basically like the language of science in this sense. So, I would assume that transformers are a really good tool to do symbolic regression with. But you said that kind of genetic algorithms dominate basically. So, why are transformers not a good tool for this? I could, for example, imagine that that like mathematics is a little bit more stricter than language, so or way more stricter.
Oh yeah, so just to repeat your question, so I make sure I got it. So why not use, or why do transformers like large language models not work for symbolic regression? Is that the question? Yeah, so there is a group that does this. Well, there's actually multiple. So I think the first one was Grammar VAE. If you're curious, it's called Grammar VAE, Variational Autoencoder. That was like 2018. They solved like a few simple problems, but nothing crazy. The bigger one recently, so there was a group at Meta AI, formerly Facebook. So they trained this like massive language model. It's funny, it's actually the same group that did Llama, if you know that language model. It's the same group. So they trained a large transformer on symbolic regression. Basically, you give it a data set and it generates the equation. It's a really cool idea. I wish it worked, it just does not generalize. So we had this like this external competition. So like none of the people in the competition would know like what the equations are, and their model was like, I don't know, it was like eighth place. So like the top three were all genetic algorithms. And I think the reason it doesn't is just because like the space of equations is like, it's funny to think about, but I think it's like actually more like it's just so massive. Like language is actually, like if you think about it, there's only so many ways you can really compose a sentence. Like there's this grammatical structure, and there's like different commonalities that you can exploit, and like different frequencies of words. But with symbolic regression, there's no like limits on what you can have in an equation. And every single time you do a mutation, you get a completely different function. Like you change a multiplication to an inverse, and it's like completely different. So it's this very nonlinear search space. And I think that is part of why it's hard to pre-train on a randomly generated set of equations. I think the mixed approach is probably what you want to do, because that's what they use for AlphaGo. So if you remember the AlphaGo, they use this like Monte Carlo tree search. So you have this network that kind of predicts like what is the best next move. It doesn't like tell you the whole game, kind of, right? Like it tells you, okay, what's the next best move? And then you have this like search through the tree space. I think that kind of approach is really good for this. So there's been a few papers looking at this for symbolic regression. It's just like, it's pretty hard. I think the reason it hasn't really been done is just like an engineering challenge. Like it's already hard to build a genetic algorithm that is very efficient. Yeah, to actually do like Monte Carlo tree search with like a learned reinforcement learning algorithm is just, it's a hard engineering challenge. But I think that is kind of like the best direction to go. But like a pre-trained transformer just doesn't seem to work that well.
One more question, yeah.
Well, it's a bit provocative, but it seems to me that the planetary example, I mean, all of the physics is in the fact that forces are the relevant part, like the relevant thing to model the problem, and the fact that forces are variables. If you started doing like three-body interaction, then you would never convert a problem.
Yeah.
So it seems like there is a lot of biology that you put into the network, right? And still you have to manually adapt.
Yeah, so just so I understand the question, because the audio was cutting out a bit. So the question is, why is it, or I guess like, is it safe to assume the two-body interaction? And I guess like, would that limit the space of discovered models? Is that kind of the question?
The question is more like you kind of type the answer to the network.
Yeah.
Yeah.
Yeah. So yeah, so that is a oops, sorry, I stopped sharing, one sec. Oh no, now my face is massive. Okay, go to this. All right, so go to, so yeah, like one of the, so I mentioned like a way to break this degeneracy is have a specific inductive bias here, like maybe a sum over particles. That is a big assumption. And I mean, you have to make that assumption. You have to have some way of limiting the space of models. Otherwise, it's just like, it's too large. And I mean, oftentimes there is a clear choice. So here we are assuming, so in the Newton example, we're assuming it's a Newtonian force law, which again, you can study on Earth. You don't need, so it's not like a circular problem. So it is kind of like, okay, if we make this assumption that it looks like a regular force law, what is the dynamical law? And you can test that, right? Like you can see, okay, did it give us good predictions? And so I think if you're dealing with an undiscovered model, what you could then do is say, okay, does this inductive bias work? So you make some choice, maybe based on your current models. We make like similar assumptions. Does it work well? If it doesn't work well, you could kind of change it, try a different inductive bias, and kind of explore that space while doing the symbolic distillation. Another thing you could do, so this is what we did in this paper, is actually, so these equations, even though it's a sum over this scalar term, actually the model, we didn't tell it that. Like this is an unknown equation. The only thing we imposed that it's a sum over particles, but it's actually started as 100-dimensional vectors. And what we did is we learned the correct inductive bias. We learned, so we trained with a sparsity penalty, basically. So we said, okay, the network is penalized the more variables it's summing. And so the network has to like compress it to 1, which happened to be a good fit. But I think like that kind of approach is good. So you could think about, okay, like maybe it's a sum, like maybe if you want to involve 3-body interactions, you could actually add that as another term and just like regularize it. So the network has to pick 1 and kind of like, okay, 3-body interactions are better. Actually, there's another cool paper from Jesse Taylor's group that shows if you have a high dimensional space in a deep set, even though you start with 2-body interactions, you can actually compute 3-body interactions kind of like implicitly. It's a cool paper. It's called like energy flow networks or something. Yeah, I think generally, like I would just say, if you really don't know the inductive bias, you could try learning it. So you could set up like all the different ideas and then train the network so it has to like eventually choose one of the inductive biases. Yeah. But yeah, it's a really like that's kind of the trickiest part about this approach. It's the choice.
Okay, thank you. Any other questions? If not, let's thank Miles again.
Okay, thanks. Yeah, see you tomorrow. Bye.
We have dinner here. I'll write it here later. I think what's good. Talk to you later then.
Okay, bye.